Putting this all together, we've developed a simplified automated testing example. The goal is to completely drive the ASL ventilator testing through a standalone software application. The application is built in Visual Studio environment using C# programming language. In the example, we've created 3 simple tests that provide some idea of how the TAI can be embedded into the development or testing process. The first 2 tests are simply comparing the ASL's output with that of the ventilator's output. Test 1 runs 5 breaths in volume control mode, then produces a waveform. Test 2 runs 5 breaths in pressure control mode, then produces a waveform. And the third test is geared at triggering and validating alarms from the ventilator. Here, we use the interactive control option to increase resistance during the simulation to force the ventilator to alarm. Our goal is to trigger the low tidal volume alarm by reducing flow to the vent by increasing the resistance over time. Here are some code snippets showing the TAI command in use. As stated in the previous slide, we use the Visual Studio environment with the C# language. The design is made with WPF, MVVM, WinForms, and a third-party toolkit for the controls and waveform charts. Here is an example of how we invoke the BP command. We created the webinar breath parameters class, where we're calling 4 of the 100 plus parameters: tidal volume, peak pressure, breath rate, and PEEP. And you can see the TAI command and parameters in the orange script. Here's another example of how we invoke the BW command, or the breath waveform command. We created the ASL breath waveform class, and here we are parsing the output from this command to plot it inside of our GUI. Here's the example application we built for the webinar. It lasts about 3 minutes. In that time, I'll be pointing out some of the features. After the video completes, we will move to the questions and answers. On the left side of the screen is where we are constantly monitoring the application for any errors and recording everything for logging purposes. The right side of the screen captures outputs in a more elegant manner. As the test begins, you can see some of the TAI commands being invoked. SF is used to load our initial file, which is a passive patient. The TC command to capture versioning details. The BP command, which will pass data to the GUI for each breath. We also have ventilator commands being passed in terms of setting up the modes and initial conditions. On the right of the screen is our GUI, which is compartmentalized for easier feedback. On the bottom left, we have indicators to know we are connected to the ASL lung and to the ventilator. Above this, we're displaying the version information about our software, TAI, and lung firmware, as well as the ventilator information. This comes from the TC or tell condition command. We've chosen to plot the pressure, volume, and flow after each test completes in the chart area. At the top of the GUI, we have LEDs to monitor ventilator alarms. Below the alarms are data outputs from the vent, volume, PEEP, and PIP, and from the ASL, rate, breath number in the simulation, and the set resistance value, which is used in our third test. Finally, we can see the ASL and ventilator outputs next to our alarms. As I've been explaining this, we've completed 2 tests that could be based on comparing tidal volumes or peak pressures for 2 different modes, volume control in test 1 and pressure control in test 2. In the third test, we wanted to verify alarm limits. Here, as the simulation runs, you can see the IC command being invoked. Our volume limit for this test is 300 milliliters. As we increase the resistance in the lung, we expect a reduction in flow and thus a reduction in volume. In the log screen, the initial resistance was set to 6 centimeters of water per liter per second, or a healthy patient. And as the simulation progresses, you can see the IC command increasing the resistance to 21 centimeters of water per liter per second. And as this change is invoked, we can notice that our volume drops below 300 milliliters, causing the low tidal volume alarm to become active. And our simulation will end with another waveform that depicts the patient's breath that triggered the original alarm. This concludes our demonstration of the TAI being used in a testing environment. Thank you for watching.